Hello everyone. I hope you're having a good day and I hope that the sun shines on your business today. I'd like to thank you for attending this webinar on ultra-accelerated weathering. And sometimes it's good to start the day off thinking about new ideas, and what I'd like to talk about is new. Ever since I began working in weathering technology, there's been a great urgency expressed by users for faster results. And today we're going to review a new class of weathering technology born from those requests, and review considerations for conducting research in ultra-accelerated weathering, a new experimental technique. We'll talk a little bit about how this experience came about by way of introduction, and then discuss a number of considerations relating to this work, including energy balance considerations, a new device in this class and how it works, correlation and acceleration, of course, reciprocity considerations, irradiance calculations, customization alternatives for the new device, and of course how you can get additional information. Now, as a general housekeeping item, I need to mention right up front that Atlas is in the process of publishing a considerable amount of information related to this topic, and as those efforts proceed, we'll be able to distribute more information to wide audiences, but for now we'll not be able to provide copies of this presentation. If you need to communicate specific information to individuals, for example, to support a project's efforts, please give me a call and we'll try to figure out an appropriate alternative. We do, however, have a technical publication describing much of this material that we'll be happy to provide you with. Just let us know. And my contact information will be on a slide at the end of this presentation. I'd like to talk just a little about this great experience I've had working on this project and the organizational efforts that made this possible. Much of the effort was sponsored by the Department of Energy under a program called IPP. That stands for Initiatives for Proliferation Prevention. And when the Berlin Wall came down and the former Soviet Union became newly independent states, there were a number of very highly skilled weapons of mass destruction scientists that needed a paycheck, and the U.S. government felt it might be better to get that paycheck for working on non-weapons related work. So the DOE set aside some funds to bring together private U.S. industry, Russian institutes, and U.S. national labs to work on joint projects. And the device that we'll highlight today was a direct result from that work effort. And Atlas has been very fortunate to participate in this joint program with the Institute for Laser Optical Technology, that's located in Moscow, and the National Renewable Energy Laboratory, located in Golden, Colorado. And some of the world's best and most experienced scientists and institutional infrastructure has been brought together to look at this issue of ultra-accelerated weathering under this project. And as we begin this presentation, I'd like to take my hat off and thank the people that put together the IPP program, as well as the institutions and scientists that collaborated on this effort. It's truly a great event at several levels of context. Now, speaking of context, I have a general comment on the content you'll see this morning. We're going to review considerations for ultra-accelerated weathering from 2 points of view, both general and specific. In general, these considerations can be applied to any accelerated methodology. There are a number of ways to achieve weathering results very quickly, and certain principles apply no matter what technology is involved. But specifically, we're going to review methodology using a new commercial device that was developed under the IPP program, and experience with the ultra-accelerated weathering system, or the UAWS, really highlights the more general considerations. So if you think both about general considerations as well as specific aspects as the presentation unfolds, it might provide more value. Well, to begin, let's set the context and talk about what we mean by the term ultra-accelerated. As we look back across weathering methodology, we can group approaches into 3 general categories with similar sets of considerations. We can talk about real-time weathering, we can talk about moderately accelerated weathering, and most recently, ultra-accelerated. Now, real-time weathering methods are by far the most accurate. In real-time methods, we simply place material specimens outdoors in the end use or worst case use natural environment. And here we can see specimens in Florida and Arizona exposure labs. Now the material behavior in real-time weathering forms the baseline or reference for service life, and real-time exposures are required for all material weathering programs. Now one critical element of real-time exposures for meaningful interpretation is a measure of duration. Often this measurement is radiometrically determined. That is, material changes are measured as a function of light exposure. Light's often the critical variable affecting service life, typically ultraviolet or UV light. Now keep in mind, material degradation behavior is usually characterized as a degradation curve with property change on the y-axis and UV radiant exposure on the x-axis. So radiometry is typically a key part of weathering studies, and it has to be carefully considered. And here we can see an example of UV radiometers at an outdoor exposure lab for measuring UV radiant exposure. Now, as I mentioned, these real-time methods are the most accurate, but at a cost of a very valuable asset, time. These are slow. So for just about as long as man's been doing weathering studies, he's been trying to speed up the process of obtaining weathering results. And there have been some pretty interesting approaches developed. Here's two examples. In the artificial light weatherometer cabinets that Atlas has pioneered, a light source designed to match the solar spectrum can expose specimens to UV, even at night. And this, with a slightly higher intensity of UV, can result in a moderate acceleration in the rate UV is deposited on specimens, or radiant exposure. An environmental chamber maintains specimens at reasonable temperatures. Now in the outdoors, solar concentrators we call EMA, which stands for equatorial mount with mirrors for acceleration. In this method, the UV light is even more intensified. In this method, multiple images of the sun are reflected into a single target area where specimens are placed. Now, of course, as the total solar light is intensified, so is the heat load. So blowers are used to maintain specimens at reasonable temperatures. And we'll talk more about this device for comparison, but we'll refer to this as EMMA, E-M-M-A, for equatorial mount with mirrors for acceleration, or we may refer to it as the ASTM G90 outdoor test method. But keep in mind that with all these existing methods, the radiometry for actually determining the radiant exposure is a critical part of the methodology. Even with these moderately accelerated methods, society in general and industry specifically has demanded more acceleration, a lot more. And recently, technologies become available to push UV radiant exposure rates even faster. And now we see a number of new approaches for achieving even faster rates of UV radiant exposure, and we're grouping these into the ultra-accelerated category. For example, many researchers are taking advantage of the inverse square law of light and moving material specimens much closer to artificial light sources to increase UV intensity. Conversely, many researchers are increasing the UV light intensity with new and more powerful light sources and power supplies. And finally, researchers are building very sophisticated solar concentrators and exposing specimens to concentrated natural solar UV, and we will discuss considerations for these methods in depth today. So we can see this general developmental trend in weathering technology, but I want to emphasize 3 points. First of all, these methods should be used in concert. No good weathering researcher using accelerated methods should depend on the results of a single methodology. It's the preponderance of evidence from different data sources that should be used to characterize weathering behavior. The second point is that this real-time weathering is not optional. It's a requirement for good weathering research. It is the baseline. It's the reference for good weathering researchers, and good weathering researchers always precede accelerated weathering with real-time weathering. And the third point is the radiometry. The measurement of UV radiant exposures in these methods is always a critical consideration. So with these general considerations mentioned, let's begin to discuss some more specific elements. Now, you know, solar concentrators have a great history of work in chemistry. This one was built in 1772 by the French Academy of Sciences. This is the one Lavoisier used, and Lavoisier is considered the father of modern chemistry, and he used this one to work out the oxidation-reduction reactions, which were the starting point for modern chemistry. And it's kind of ironic that what we're trying to do with our ultra-accelerated weathering concentrators is almost the exact inverse of what Lavoisier was trying to do with this. He was trying to generate great heat in the absence of oxygen in order to reduce oxides. We are trying to oxidize materials in the absence of heat in order to photooxidize rather than thermally oxidize materials. And anyone who's ever started a fire or melted a piece of plastic with a magnifying glass knows things heat up under solar concentrations. Well, how do we keep things from getting too hot under concentrated sunlight? Well, that would be the 400-pound gorilla sitting in our laboratories. So let's talk about this for a few minutes. I believe weathering researchers need to become experts in the application of the energy balance expression. And we'll look at this expression in two different ways. In general, what this expression says is, at steady state temperatures, the energy that goes into a material must come out of a material. On this side, we represent the energy coming into a material. That's Q, that's the solar radiation. That's alpha, that's how much of Q the material will absorb. So this is the absorbed radiation from the sun in the material. And this side of the expression shows how energy is released back into the environment. And there's slightly different forms of this depending on the conditions. I know different researchers use slightly different forms, but basically we have three different terms in this side of the equation showing how heat energy comes out of the material. Now this first term up here shows convective cooling, and this case has two sides, so heat can come off the front and the back side of the material. Now these are radiative terms for the front and the back side. So this case here shows a heated material standing in air, cooling convectively and radiatively. Now if you choose to change the cooling style, for example, maybe by putting a chiller plate behind the material, you just correct the terms. You drop one side of the convective and substitute this conductive term for the backside radiative term. Now, traditionally in outdoor concentrated solar weathering, the industry has always addressed this side of the equation, specifically the convective cooling term. But what we wanted to do in this project is to start working with this side of the expression, specifically with Q. And we knew that we could dramatically reduce Q by getting rid of parts of the solar spectra that weren't energetic enough to cause photooxidation. That's the visible and the near-infrared portion of the solar spectrum. All they do is vibrate molecules and cause heat. And if we could filter out the lazy visible and infrared photons, we'd be left with a Q that had all the energetic photons that cause photooxidation and none of the lazy photons that do nothing but heat up the material. You can think of Q as light beer. It has all the effect with only 1/5 of the calories. You're still going to get a lot of heat, but much less than you would with the entire solar spectrum. Let's look at this expression in a different way. This is the same expression but solved for a specific case, the black panel temperature. And we're looking at this on an EMA device. Now, even with no cooling, we can see a big reduction in temperature across all different concentration factors just by filtering out infrared from sunlight. Now, most of our clients are a little concerned about exceeding a maximum end-use condition temperatures, so they give us a hard ceiling right around 80 degrees C. And now our job is to exploit that energy balance equation and bring these black panel temperatures under 80 degrees C at these high concentrations. Well, one of the easiest things we can do is simply add some convective cooling air. And if we add a 37 mile per hour blown air onto the black panel, we can achieve these reductions as predicted by the energy balance equation. And if we do that with natural solar, we achieve predictions of our EMA exposure. These dashed lines now show the condition when we add convective cooling to the total solar and add convective cooling to the UV only temperature predictions. Now this line here is what the energy balance predicts with the EMA, the ASTM G90 method. The observed EMA is shown by these green points, and we observe our EMA black panel temperatures just below the critical temperature with a slightly less than 10 solar concentration factor. And it's nice when theoretical prediction is confirmed by empirical observation that we see here. But what the energy balance also says to us is that if we would substitute UV-only mirrors on our EMA machines with convective cooling, we could go out to about a 20x solar concentration. Now, if we add backside conductive cooling to our EMA devices, the energy balance says that we could go all the way out to a concentration of about 30 in our existing EMA, just simply by adding convective front-side cooling and conductive backside cooling. But look what happens if we can do the same thing with UV-only mirrors. The energy balance says that we can achieve these ultra-high concentrations and still keep reasonable black panel temperatures. So that's the theory behind this project. As anyone who's ever worked with me will tell you, I'm not a theoretician. I'm an experimentalist because I know the devil's in the details. The theoretical predictions are always based on assumptions that don't usually appear on the PowerPoint slides. So how does it really work? Well, we went and built some amazing mirrors that transmit visible and infrared but reflect solar ultraviolet onto a sample. Now the mirror surface is made up of many layers of two materials with very different refractive index. And at specific thicknesses, the change in refractive index will reflect specific wavelengths of light. You build up layer after layer on glass by evaporating metal oxides onto the surface under a very high vacuum. And you alter the thicknesses of the layers to obtain specific reflectance spectrum. It took a lot of long, painstaking work by our Russian partners to do this, but we finally ended up with this reflectance spectrum for these mirrors. And as you can see, the mirrors do not reflect much of the infrared, but have very high reflectance in the solar UV. And the result is you will not reflect the wavelengths that only result in thermal load, and you'll end up with reduced Q. But we still need to keep the wavelengths from the solar spectrum that have enough energy to break the bonds and initiate photooxidation. So we built a concentrator using these amazing mirrors. We used 29 mirrors in the concentrator design, and we shaped the surface of the mirror to a radius of about 10 meters. So these are focusing optics with a 5-meter focal length. And we placed each facet on a 10-meter radius support structure. And then we placed the target area about 2.5 meters towards the focal point. And this is what we came up with. We can see that we have a support structure for the facets, and the support structure has about a 10-meter radius designed into it in both the vertical as well as the horizontal axis. You can see the curvature of the concentrator here. We've got facets that also have a 10-meter radius cut into them. And then we mount these facets onto the support structure. We mount the support structure onto a tracking mount that will allow this to follow the sun. And then we place a target area out where we will be focusing the solar radiation. Now there's two distinct features that I want to point out about this design. The first feature is the target area is not all the way out at the focal point of the optics. We have the ability to move the target area further back and achieve even higher concentrations than we'll talk about today. But there's a sacrifice in target area the farther towards the focal point that we move the target area. So there's this inherent trade-off between concentration and target area. The second feature is that I can independently align these facets. So I can have one target area at 100% concentration, or I can split the alignment, have these two facets pointed over at a different target area here, and have two target areas at 50%, or one at 25%, another 75%, or four at 25%, and so forth. So this is a very flexible design. Here's the flux map that NREL made of the Atlas device just after installation. This is at 100% concentration. And you can see that within the 15 centimeter by 15 centimeter design target area that we were able to achieve some very good uniformity in the target area. Now one final note on that mirror surface is the evaporative coating appears extremely robust. 8 years ago I attached one of these witness coupons to the mirror bed of a traditional EMA machine, and that sample had seen sun and rain and dirt and washing and abrasion, but it's still within the error of the narrowband UV reflectometer measurement. It's shown no measurable degradation. Well, whenever you introduce a new weathering technology, usually the first comment you get is something like, "Show me some examples of correlation." So that's what we'll do now. For initial studies, I wanted to show some materials with very different characteristics. So I chose a reflective paint and a transparent plastic to work with. And these two are very different classes of materials. This is a thin film, this is a thick plastic. I needed some initial data quickly, so I used a fast and moderate rates of change. I wanted a material that obeyed strict reciprocity. I wanted another material that didn't, and we're going to talk a lot more about reciprocity in a minute. I also wanted materials that have been exhaustively characterized, were instantly recognized by the industry, and were readily available for anyone who wanted to confirm my work. Which led us to the Urethane standard reference material and the polystyrene standard reference material, which fulfilled all the requirements and are specifically meant to be used as reference materials for testing weathering methods. Now the Urethane is a European standard reference material, and it's produced by EMPA. It's a pigmented thin film, a paint of melamine resin with a sepia pigment on aluminum. It's been very highly characterized for color change as a function of UV exposure. Now the polystyrene is a United States standard reference material produced by IFAI. It's a thick, visually transparent thermoplastic, again, highly characterized for color change as a function of UV radiant exposure. Well, most people ask about correlation, but what I know is they want to see both the quantitative correlation, which tells us how well the new device simulates the natural degradation function, and also acceleration data, which tells us how fast the device will perform that simulation. So we're going to look at two sets of graphs, one with the x-axis normalized across different exposures by radiant energy in joules UV, and then we'll look at another graph with real time on the x-axis. And we're going to compare some real time, some moderately accelerated exposures to ultra-accelerated exposures. Here we have a correlation graph comparing different exposures of the Urethane SRM. So in this correlation graph, we're normalizing for UV radiant exposure, or megajoules per meter squared UV, on the x-axis, and then the y-axis, of course, is the property change as a function of UV exposure. And here are three exposures: natural, real-time. The RTs are real-time, and they are in Florida and Arizona. And we also included a moderately accelerated exposure, the EMMA, which is also in Arizona. That's these three exposures here. Now the red diamonds show that the ultra-accelerated exposure follows the Arizona real-time exposure very well. It really just doesn't get any better than this. And then you say, well, that's great. But how long did that exposure take in days? How accelerated was it? So now we're going to change the x-axis to days. And what we see is that what took about 140 days in the real-time exposure took only 1, 2, 3, 4 days on ultra-accelerated. That would have taken about 60 days on the moderately accelerated EMMA. So these two graphs, the correlation and acceleration of Urethane, were the results of the first experiment on the new device. But it's not just a matter of exposing things to high irradiance. Anyone can simply pump up the energy. Anyone can move a sample closer to a xenon source, use the inverse square law, or expose to multiple metal halide sources, or use more reflected images of the sun. The trick is exposing specimens with ultra-high irradiances with ultra-high fidelity to the natural spectra without the specimens melting or burning. That's the trick, and it's not easy. And anyone who's run the energy balance calculation or done the empirical work knows it. But what's this bit here about spectral fidelity? Well, in an extraordinary set of publications, Ford Research put forward what is pretty much now a generally accepted hypothesis, that in order to get the weathering photochemistry right, you have to get the light source to mimic the outdoor natural solar spectra. So Ford watched chemical changes in the natural weathering and compared the natural weathering chemical changes to the chemical changes under artificial light sources. Now, one of the light sources showed exceptionally good simulation of the natural photochemistry, and that was the concentrated natural sunlight in EMMA, the ASTM G90 method. Now, since this work, Atlas, Ford, and Schott have developed a right light filter for use at moderate xenon acceleration. But their point in this graph was that deviations from the natural solar spectra may result in unnatural weathering chemistry. Any deviation from the natural solar spectral distribution may not appear significant at moderate accelerations, but may very well become significant at ultra-accelerated intensities. This red line is the sun. That's unaccelerated. The yellow line is a 5.5 times acceleration of the solar spectrum. Now, if you're trying to simulate the red and you miss a few of these ridges and valleys, or the proportions of the ridge to the valley, it might not be a big deal at natural real-time intensities. But when you go up to 5.5 times, any inaccuracy will also be intensified. Now, keep in mind that the new device we're working with now is an order of magnitude greater than EMMA, so fidelity may be extremely important. Well, now let's take a look at a completely different standard reference material with different weathering characteristics. Here is the acceleration graph for polystyrene. We see days on the x-axis. And what we see for polystyrene is that what took about 115 days in Arizona real-time exposure took only 1, 2, 3 days on ultra-accelerated. That's fast. And at some point, we may have a problem because things are changing so fast, we can't measure them with the proper frequency. Okay, great. Acceleration for polystyrene. Now what about correlation? Well, we normalized the data by radiant exposure on the x-axis, and on this material, we see departure from correlation. And although I've seen worse correlations published, and these trends are still going in the correct direction, well, we need to figure this out and understand what's going on here. This is where some in the industry go, well, let's skip the quantitative and use the Spearman rank correlation. Well, this is where we begin to talk about the other 400-pound gorilla sitting in our laboratories. I first published on reciprocity in 2004. I wrote another paper on it in 2005 and a third in 2006. The concept of reciprocity is a foundational concept of our industry, and it influences our science whenever we time two different exposures by radiant energy or dosage, or plot two different degradation curves with joules on the same axis, or infer the equivalence of 300 megajoules of UV in artificial with a year in South Florida, or use a pulsed xenon source. It's the unspoken industry standard of operation. It's an underlying assumption of much of the current weathering methodology. It's really the wisdom of the herd that's helped us evolve through moderate acceleration. When I began working with this, NIST referred to it as the law of reciprocity. And it's really a simple logical concept. Materials react to energy, and energy is the product of intensity times duration. An exposure at twice the intensity for half the time is the energy equivalent to an exposure at half the intensity for twice the time. Watts, that's intensity, times seconds, that's duration, equals joules, energy. And we time exposures in joules of UV. But at this point, the conventional wisdom of our industry makes a logical leap, and it says that within limits, these two exposures are equivalent, and they should result in the same property changes, all other things being equal. The within limits being that you can't get the intensity so high that you burn the materials, for example. Well, you can characterize that concept in a function which has a characteristic shape and has the variable raised to the power of -1. That is a mathematical definition of strict reciprocity. But around 2002, something happened to me that made me begin to doubt the human logic behind this universally accepted assumption. It required that we actually invent the apparatus we needed to study it, which, by the way, is patented temperature control EMA suite of products at Atlas. We even have a patent on the methodology. So we tested our hypothesis with our new devices, and we compared predictions under the assumption of strict reciprocity with our observations. And once we had our data in a pile, we published this data at the Sedona Service Life Prediction Symposium. Now in this data, I normalized it to the results of a 10-mirror EMA machine. And I watched our observed values deviate from reciprocity as I removed pairs of mirrors while holding temperatures the same between these different exposures. The paper said that this strict reciprocity is no longer a valid assumption. We have observed significant deviations in controlled repeatable experiments. And after I showed this graph, several other researchers stood up and confirmed the observations, saying they were using very similar values like -0.63 as the exponent of their service life prediction models. Now I showed one more graph at the end of the presentation. That slide hypothesized what would happen if you took the intensity way out to ultra-accelerated levels. The crossover point here on this graph is a 10-mirror EMA device. That's moderate acceleration. And the pink dots are the observed deviation from reciprocity. And if you follow these curves all the way out into ultra-accelerated land, the assumption of strict reciprocity predicts that the polystyrene will degrade about twice as fast as the prediction calculated with the observed deviation from strict reciprocity. The strict reciprocity prediction is here. It predicts the end of life in about half the duration of the observed reciprocity prediction. The observed reciprocity prediction is here, about twice as long as the strict reciprocity prediction. Now at conventional method intensities, this effect can be lost in the noise. It conveniently explained away. But at ultra-accelerated intensities, this becomes a critical consideration and it can't be ignored. Well, we waited about 4 years to be able to test this hypothesis. And you see how strict reciprocity prediction takes about half of the radiant exposure of the observed reciprocity prediction to reach the same degradation point out here in this very ultra-accelerated area? Do you see how that real-time intensity takes about half of the radiant exposure as the ultra-accelerated exposure to reach the same degradation point? Well, we've got the expressions and the predictions at ultra-acceleration intensities, so we can do a back-of-the-envelope conversion of our observed ultra-accelerated results back to terms expected with strict reciprocity. And when we perform that conversion, we get this: good agreement with the unaccelerated results. The issue is not the device or the acceleration. The issue is the industry's assumption that all UV megajoules per meter squared are equal for a material. For this material, if we'd gotten data positioned anywhere else on the graph than where we observed it, the device would have been lying to us. Well, now that we're armed with this information, we can hypothesize why this moderately accelerated data right here does not fall on the unaccelerated curve, even though they're both normalized for radiant exposure. Reciprocity is not a valid assumption. Unfortunately, a goodly amount of our technology is built on that faulty assumption. At conventional intensities, deviations from strict reciprocity can be lost in the noise, the uncertainty of measurements, the radiometric measurements, the material property measurements, or conveniently explained away. But at ultra-accelerated intensities, these effects are amplified. So for whatever reason, and we've hypothesized a reason and patented a possible solution, UV at lower intensities appears to have a higher apparent quantum efficiency than UV at higher intensities. If true, this hypothesis has some pretty big ramifications in service life prediction. And this is an example of the simplest case. This is an outdoor example, outdoor end use. And so we see the sun come up, and the specimens are irradiated with low UV intensities that have a higher apparent quantum efficiency. But as the sun approaches solar noon, the specimens are now irradiated with high UV intensities that have a low apparent quantum efficiency. And this is the simplest case in the real world. Here's the case with some minor clouds. So now I'd like to welcome you all to true calculus-based weathering. This issue of reciprocity is critical in service life prediction application problems. But service life prediction is not the only use for ultra-accelerated methods. In fact, we believe some of the most valuable uses will be for material and formulation screening work. Here's some work that NREL did with the prototype device on PC polycarbonate glazing materials. Now in this exposure, NREL had two different types of polycarbonate materials. Here's type 1, here's type 2 results. One had a protective UV coating, the other did not. And NREL tested these materials at 50% of the ultra-accelerated capability, and they still obtained this data in only several months. And the manufacturer could quickly see the protection effect of the UV screen. Now these were done at two different temperatures, so they could also see the temperature variable effect. And I think it's this kind of comparative screening work that we could really target with this capability to help our research efforts. In screening work, we're looking for comparative data between materials, additives, formulations, rather than service life prediction. We're looking for weak links and poor candidates. Well, the first thing we need to talk about in calculating radiant exposure of an outdoor device is the difference between global and direct normal irradiance. Now, just like the EMA devices, the new ultra-accelerated weathering system only concentrates direct normal solar irradiance. That's light direct from the solar disk. That's called direct normal or DNI or direct normal irradiance. Specimens exposed on horizontal real-time see light from the solar disk plus light reflected back from the entire sky dome. That's the direct plus the diffuse component. And it turns out there's about twice as much UV in the entire sky dome than there is in just the direct component. That exact ratio is always changing with the always changing sky conditions. And we can look to the ASTM G90 EMA standard as a guideline for radiometric measurements in ultra-accelerated methods. And as it turns out, the radiometry methods in the EMA standard are a really good starting guideline for radiometry in ultra-accelerated solar concentrators of this design, with a very important modification. The most popular method within the G90 standard involves the use of two UV radiometers with a response in the 295 to 385 spectral region. Both of these radiometers are pointed directly at the sun and track it as it moves across the sky dome during the day. And just like the ultra-accelerated concentrator, this tracking maintains these radiometers pointed directly at the sun and follows its path. Now, one of these UV radiometers measures the light direct from the sky dome, both the light direct from the solar disk and the light reflected from the blue part of the sky, the diffuse component. The other radiometer measures only the diffuse component. It has a shading disk which excludes the direct normal component. It excludes that 6 degrees circumsolar part of the sky. So only the diffuse energy is measured. Well, once we measure the total component and the diffuse component, we can simply subtract the diffuse UV from the total UV to observe the direct normal UV. Total minus diffuse only equals direct. So now we have the direct normal UV, which is the only light the collector reflects onto the specimen. And this is all clearly outlined in the ASTM G90 with diagrams and explanation. Well, the next thing you do in the G90 procedure is to take this incoming direct normal UV and multiply it by the concentrator's optical constants. So you multiply the incoming UV by the integrated reflectance of the mirrors. And we measure and integrate that directly in our optics lab, and we saw the reflectance graph earlier. And we're using 0.95 for these facets. Okay? Then you multiply that by the numbers of mirrors. And we usually use 28 facets for 100% capability on this device. Finally, we must do one more step that's not in the G90 procedure. Since the facets have a radius, they're true focusing optics, we must also multiply by the concentration ratio. And we simply take the ratio of the reflector facet size to the target area size and use that as the concentration factor for each facet. For the geometry we're currently using, that's a factor of 4 because of that radius. So in summary, it's the direct normal UV from the shaded and unshaded radiometers multiplied by the UV reflectance of the facets that we measure in the optics lab, multiplied by the number of facets, just count up the facets that we're using, multiplied by the concentration ratio, and that's determined geometrically. And that's how we're calculating the radiant exposure on specimens in the target. Now, how's that working for us? It's great. It's easy. The infrastructure already exists at the lab. The standards community has already developed a good method. We just adapted it a little bit, and it makes perfect theoretical sense. And we're getting really good empirical confirmation. That Urethane correlation curve used this radiometric method to determine the x-axis. And if there was anything significantly wrong, the correlation graph would not have looked so good. But just to make sure, I decided to bake some of Atlas's xenocal radiometers one day. I mounted one xenocal facing the reflector, that's this one, it's in the target area, and I exposed it to concentrated direct normal light from the solar disk. I mounted an identical xenocal facing the sky and simultaneously exposed it to normal global light from the sky dome. Of course, I value my xenocals, so I only used a fraction of the concentrator facets. And this is what we find. We observed the sky dome with about 0.54 watts per meter squared incoming global UV. Now we should be able to predict the irradiance in the target area from this value. So we take our global incoming UV and we multiplied by the ratio of global to direct normal. And then we multiplied that by the number of facets we were using. We multiplied that by the concentration factor for each facet and multiplied that by the reflectance of the mirror coating. And we found a reasonable agreement between the calculated value and the observed value. Always keep in mind that the concentrator only uses direct normal light. The light we measured here is global. That's direct plus diffuse. So now that we've demonstrated confidence in the radiometry several different ways, we can discuss the radiant exposure acceleration value to the community. And we can back out an average total direct normal UV radiation from our historical measurements. And we averaged about 162 megajoules per meter squared UV direct normal per year at the laboratory. And from that, we can estimate a year's UV radiant exposure and the ultra-accelerated target area based on the number of facets, their optical concentration, and the mirror reflectance. And we average about 17,000 megajoules per meter squared UV in the target area of the ultra-accelerated weathering system per year. Now with that, we can compare back to an average year radiant exposure on 45 degrees in South Florida. We average about 275 megajoules per meter squared UV on a 45 degrees South Florida exposure. And finally, we can ratio the ultra-accelerated to the South Florida 45 degree UV radiant exposure. And this is the message we're publishing, the nameplate capability, if you will, of the ultra-accelerated weathering system. You can get about 63 years of South Florida 45 degrees UV radiant exposure in a single year ultra-accelerated. And this actually leaves us with a little additional capacity over a nameplate capability. But there's actually more to this story. This nameplate capacity is carefully stated in years, one complete annual astronomical cycle. But if you have shorter exposures just during summer, you can approximately double that ratio. In Arizona, we've measured UV direct normal irradiances as high as 23.3 megajoules per meter squared UV for the month of June. And that would have resulted in UV radiant exposures as high as 83 megajoules per meter squared UV per day on the ultra-accelerated device, which means you could achieve a year's worth of South Florida 45 degree UV radiant exposure in about 3 days in May or June. And ratioing 365 to 3 is a factor of about 122. So if you really want to get technical, we can achieve about 122x acceleration under proper assumptions. But the message that's going to come out of this lab is 63 years in 1 year. Well, how does this improve over existing technologies? Well, it should take about 63 years in South Florida, 45 degrees, to achieve the same radiant exposure as in a single year on the ultra-accelerated device. It'd take about 17 years in a xenon arc under J1960 to achieve the same radiant exposure as about 1 year on the accelerated device. I'm still working on the fluorescent, but it would take about 13.6 years on the EMMA, the ASTM-G90 device, to achieve the same radiant exposure as a single year on the ultra-accelerated. Well, by using these mirrors, we've really reduced Q, the amount of energy heating the specimens, while simultaneously concentrating almost all of the ultraviolet. But as the energy balance predicts, we've got additional opportunities to work on the variables on the right side of the equation to get the specimen temperatures where we want them. We've also developed other opportunities to take advantage of the flexibility of the ultra-accelerated weathering system platform. And for lack of a better word, I'm calling these activities customizations, since we can do different things for specific material characteristics and exposure needs. For example, the customizations we make for thin paint on aluminum will be different than for a thick, absorbent, pigmented polyolefin or transparent acrylic. Well, the first customization that we did was to add backside cooling with a water-chilled cooling plate. And here's the cooling platen in the target area, and you can see the supply and the return umbilicals to the water chiller that's in the background here. So we have chilled water flowing through the backside of the target area. And here you can see the target area, and we have some acrylic and some PMMA clamped to this backside chilling platen. There's actually two plates here. I painted one black for an experiment. And you can see this design used bolts to clamp specimens to the cooling platen. This is kind of a poor design for mounting specimens, since if you have any lift off of the specimen from the platen, it'll dramatically affect the backside conductive cooling. But using this, we were able to get reasonable exposure temperatures for some very difficult insulative materials. And here's a graph showing what we found. We simply drilled a hole into the bulk of the polystyrene, and we inserted a thermocouple into that plaque. And so here at about 9:30 in the morning, we turned on the cooling water. We were about 28 degrees C ambient air temperature at that time. And we cooled the specimen off with the cooling water. And then we focused the device at about 10:30. And we watched the temperature rise and rise and rise. And if you'd been standing out in the Arizona desert right around 1:30 on this day, you would have heard me screaming about observation not matching prediction. Well, after I had a drink of water and I took a deep breath, I found the kink in the cooling hose. And when I undid that kink, I saw this dramatic effect of backside conductive cooling. And we saw the temperatures that we equilibrated with in line with the end-use temperature and the ambient temperature here. Now here's another material where we have thermocouples sandwiched between a transparent film and a transparent cover material, and the film is against the cooling platen. And we turn on the cooling water and cool the specimen down, and then we focus the UV into the target area. And first we focused with about 50% concentration, which brought us back up around ambient. Well, then we went to 100% of the capability, 100% concentration, and we can see where we equilibrated well below that target of 80 degrees C, and we can also see the effect of breezes in the target area. So the backside cooling is very effective, but we're improving the platen. If there's any gaps between the material and the cooling platen, we have problems. And the bolt clamping exerts a lot of clamping force, but it can also cause a sample to deform. So we've developed a vacuum chuck which will actually suck the specimens against the cooling plate. Enroll developed this one and helped us develop ours very similar. It requires vacuum. Here's the vacuum manifold, but it's been shown to be a very effective mounting technique. Of course, the energy balance equation also predicts a large effect from front side cooling. So we can add some front side forced convective cooling using an axial blower. And this graph shows the effect of these two customizations. The material we're looking at here is a white insulating polyolefin. It's one of the more difficult candidates for ultra-accelerated exposure for two reasons. First of all, it's opaque, it's thick, and it's very insulative. It doesn't give its heat up to the cooling platen very quickly. The second characteristic is that the backside is slightly textured, so we don't have the material intimately against the cooling platen. So in this experiment, we drill a thermocouple into the material, and we turned on the ultra-accelerated weathering system at 100% capability, and we watched the temperature rise until we were right up at the material's critical temperature. And the first customization we tried was to drop the concentration. So we simply covered up some of the facets. You may not believe this, but Atlas was awarded a patent on that customization. It's called variable irradiance. So we can vary the irradiance and keep under this critical temperature simply by reducing the number of mirrors. The other customization I played with here is the front side convective cooling effects. And I simply held a very crude temporary blower and aimed it at the target area, and we can see the effect of convective cooling on the temperatures. These temperatures are like Arizona summer ambient temperatures, even though the concentrator is running at 100% with an extremely difficult material. And we even have more tools in our toolbox. This filter will further tune Q. And you can see here that it reflects most of the visible while transmitting most of the UV. And if we insert this in front of the exposure, it'll cut Q off down to about 450 nanometers. But it'll also drop that 95% reflectance of our facets. So I'm not sure I want to do that after working so hard to get our Spectra where it is. Another customization I mentioned before is that if a client doesn't need 100% of the nameplate capability, we can re-aim those facets to another target area. We can have as many as 4 target areas on the device. So we can have different irradiances in different target areas with different customizations. We can have a 50% target with backside cooling and a filter. We can have a 25% target with backside cooling and frontside forced convection, and then 2 12% targets with just frontside forced convection and combinations like that. Well, we've seen quite a bit of new information today, and new information is being developed every day that we work with the new ultra-accelerated methods. So how do we get more information on this subject? Well, there are a few publications from NREL describing the development of the device as well as the patent publications. We're also in the process of publishing new information in technical literature, and we delivered a large amount of technical information at the European Weathering Symposium. And we hope this is the first in a series of publications that reviews the foundational information that other technical publications can build on. However, we really believe the most important source of information for you will come from you using the system. It's like Yogi Berra says, you can see a lot by looking. We want to help you develop data around your material systems using this capability. So if you think you might like to take a closer look, please give me a call and let's discuss how we might get you the specific information you need for your testing requirements. Well, today we've looked at a variety of information, theoretical and empirical, about a new class of weathering methods. We've reviewed a number of considerations for conducting research in ultra-accelerated weathering, both general considerations as well as specific considerations of a single device. And I'd like to thank you for your attention, as well as request your comments. If you'd like more information, you can visit our website. You can contact me directly with questions regarding ultra-accelerated weathering. And finally, I'd like to thank you for attending this webinar and hope you check out some other webinars on the Atlas site. Thank you. Have a great day.